Hello, Matt here from chemistrystudent.com. In this video, we're going to look at enthalpies of solution. We're going to talk about what enthalpies of solution are, the link between enthalpy of hydration and lattice dissociation, and show how enthalpies of solution and hydration can be used to find lattice dissociation and formation enthalpies. Lattice enthalpies and Born-Haber cycles have been covered in separate videos. Check the links in the description below. Before we talk in detail about enthalpies of solution, there are a few essential ideas you need to be comfortable with. Enthalpy change refers to the change in heat energy of a system or substance during a reaction or process, measured at constant pressure. It is shown as delta H. Standard enthalpy changes are used to ensure enthalpy changes can be compared for different reactions and processes. A measured enthalpy change can be considered standard if standard conditions are used and reactants are in their standard states. Standard conditions are 298 Kelvin and 100 kilopascals. Standard states are the physical states of substances when they are at standard conditions. Ionic lattices form by the attraction of oppositely charged ions to each other. Lattice enthalpies of formation refer to the enthalpy change that occurs when a lattice is formed from its constituent gaseous ions. Standard lattice enthalpies of formation refer to the enthalpy change that occurs when 1 mole's worth of an ionic lattice is formed from its constituent gaseous ions under standard conditions. As energy is always released when lattices form, lattice formation is exothermic and enthalpies of formation are negative. Breaking apart the lattice, called dissociation, is endothermic and lattice enthalpies of dissociation are positive. The value for both enthalpy changes is the same for a given lattice. The only difference is the positive and negative. Hess's law tells us that the overall enthalpy change for the conversion of a set of reactants to products is the same, regardless of the route taken, assuming initial and final conditions are also the same. It is possible to find the enthalpy change for a part of a route if all other enthalpy changes are known. This can be done using Hess cycles. Born-Haber cycles are a type of Hess cycle that can show two possible routes for the formation or dissociation of an ionic lattice. Recap done? Let's go. When a solid ionic compound, lattice, dissolves in water, the temperature of the water usually increases or decreases slightly. This shows us that as a solid compound dissolves, an enthalpy change occurs. This enthalpy change is referred to as enthalpy of solution. The actual enthalpy change that occurs will be based on the type and amount of solid dissolving, meaning we define enthalpy of solution as 1 mole of a solute dissolving in water to form an infinitely dilute solution. The infinitely dilute solution part just means that if any more water molecules were added, there would be no impact on the enthalpy change that is occurring. The fact that an ionic lattice can break apart so easily when added to water is really rather strange. We know that large amounts of energy are needed to separate the ions in a lattice. This can be seen with the high melting points that ionic compounds usually have. Sodium chloride, for example, has a melting point of 801 degrees Celsius. That's high, and a lot of energy is needed to get sodium chloride to that temperature. Why then, at only room temperature, can a solid lattice of sodium chloride break apart so easily when added to water? The other puzzling question is that if so much energy is needed to break apart the lattice, why doesn't the temperature of the water plummet and the water freeze? Because the energy to break apart the lattice has to come from the water. The fact that the temperature of the water changes only a little bit and can sometimes even increase for other compounds dissolving means energy must also be released from somewhere to offset the energy needed to break apart the lattice. This releasing of energy comes from the forming of bonds and forces of attraction between the ions freed from the lattice and surrounding water molecules. Bond forming is exothermic and releases energy. To answer this question of how lattices dissolve so easily, we can model the dissolving of an ionic compound in two parts or steps. First, the ionic lattice itself has to be broken apart completely into free ions. Energy is needed to overcome the forces of attraction between the ions in the lattice to enable them to dissociate from each other. The second part of the dissolving process is the forming of bonds between free ions from the lattice and water molecules. This is referred to as solvation or hydration. We can't actually measure the enthalpy changes for each of these two steps occurring, as they effectively happen at the same time. Bonds between water molecules and ions form at the same time as the ions themselves break away from the lattice. To find any type of enthalpy change then, we will need to use Hess's law and a Born-Haber cycle. By constructing a Born-Haber cycle, we can see that there are two possible routes we can use to break up a lattice and end up with hydrated ions. Firstly, we can simply dissolve the ionic lattice in water. For this example, we'll use sodium chloride again. This would be enthalpy of solution, and as mentioned, refers to the enthalpy change that occurs when 1 mole of the ionic compound, NaCl, is dissolved in water to form an infinitely dilute solution of Na+, aqueous, and Cl-, aqueous ions. This enthalpy change is easy to measure and can be found experimentally. The second route is a bit trickier and involves turning the ionic lattice into its gaseous ions of Na+ and Cl-. This would be lattice dissociation enthalpy, impossible to measure. Then we mix these ions with water or hydrate them to form an infinitely dilute solution, again of Na+, aqueous, and Cl-, aqueous ions. This would be enthalpy of hydration and can actually be found experimentally by hydrating 1 mole's worth of each gaseous ion independently and then combining these two enthalpies together to give us an enthalpy of hydration. By using this Born-Haber cycle and Hess's law, we can see that the enthalpy of solution for a compound is the same as its lattice enthalpy of dissociation and enthalpy of hydration of ions in the lattice. As we can measure the enthalpy of solution and enthalpy of hydration, we can use these values to find the lattice dissociation enthalpy of the lattice. As lattice dissociation enthalpy is the same value but with an opposite sign as lattice formation enthalpy, this method can be used to find lattice enthalpies of formation. This is why you may see minus lattice enthalpy of formation written instead of dissociation in the cycle. For many lattices, the lattice enthalpy of dissociation and of hydration is very similar, meaning very small enthalpies of solution. This is why there may be very little temperature change when a lattice dissolves in water, as ultimately very little overall enthalpy change actually occurs. And this is partly why dissolving can sometimes happen so easily at room temperature for many ionic compounds. So, to summarize, when an ionic compound dissolves in water, the temperature of the water usually increases or decreases slightly. This shows us that as the solid ionic compound dissolves, an enthalpy change occurs. This enthalpy change is referred to as enthalpy of solution. 1 mole of a solute dissolving in water to form an infinitely dilute solution. By constructing a Born-Haber cycle and using Hess's law, it can be found that the enthalpy of solution for a compound will be the same as the lattice enthalpy of dissociation, or minus lattice of enthalpy of formation, plus enthalpy of hydration. The lattice enthalpy of formation of an ionic compound is the same as the enthalpy change of solution minus enthalpy of hydration, all times by -1, as lattice enthalpies of formation are exothermic and have the opposite sign to a lattice dissociation enthalpy. Compared to lattice enthalpy of dissociation and enthalpy of hydration, enthalpy of solution is usually very small. This means for some ionic compounds, very little temperature change is observed as it dissolves in water. I hope you found this video useful. Please check out other relevant videos given in the links below and visit chemistrystudent.com for free notes and revision materials.